Hello, everybody. My name is Tony, and today, me and my teammates, Daksh and Anjali, we're gonna talk about card shuffling analysis. So, what we're gonna talk about today is what is card shuffling, some historical background, card shuffling analysis, and the type of card shuffling. And we're gonna talk about how we use Markov chain in, to do the card shuffling analysis. So card shuffling is the procedure used to randomize a deck of playing cards to provide an element of chance in a card game. So in the 820 AD, the card game was invented in China, and it used to be like a currency. And then from the early 14th century till today, the card game is what we know today. And in America, they introduced to the world the new Joker card. So the main question that we're trying to answer today is how many times do I need to shuffle a deck of cards to make it totally randomized? So for that we need to study the procedures and analysis a few shuffling methods. So type of shuffles. So number one type of shuffles is top in shuffle. So if I have a deck of cards and I hold it in my hand, so I take the top card and I insert it randomly in a different position in the deck. Number two type of shuffles is refill shuffle. So I split the cards into two halves and mix them together. So for the top in shuffles, so you take a card from the top from an end position and you insert it in randomly in the deck of n-1 left cards. So the total number of ordering for a deck is n in n cards will be n factorial. So if we have an example about three cards, if we have 1, 2, 3, so what is the probability if the card is 1, 2, 3 is 1 over 3? And if I take the first card, number 1, and insert it in the middle, it will be 2, 1, 3, and it will be 1 over 3 again. If I take the first card from 1 to 3 and insert it in the end, it will be 2, 3, 1, so the probability will be 1 over 3 again. So what is permutation and shuffling? So let's say, for example, we have 5 card deck and we can do a permutation, P1. So let's say that we have 1, 2, 3, 4, 5. So I take the first card and put it in the end. So P1 will be 2, 3, 4, 5, 1. And let's say another example, P2, we have 8 cards. So let's say that we're going to perform a refill shuffle on them. So let's say that I have a deck from 1, 2, 3, 4, 5, 6, 8. I cut it in the middle, so I have the first half 1, 2, 3, 4, and the second half 5, 6, 7, 8. So the first card will be the first card from the first part, it will be 1. The second card, it will be the first card from the second half, it will be 5, and so on. So in the end, I will get a shuffle with 1, 5, 2, 6, 3, 7, 4, 8. So let's say that we have P3 as well, and it includes 5 cards. And let's say that the ordering of it is 5, 4, 3, 2, 1. So if I do a convolution between P1 and P3, I will get the reverse. So if the reverse of P3, so if the P3 is 5, 4, 3, 2, 1, I will get the last card, it will be in the front. So it will be 1, 5, 4, 3, 2. And then if I do a permutation and convolution between P1 and P2, so I will get the formula Q1 times Q2P, it will be the summation of Q1 P1 times Q2 P1 to the power of -1. Now I'm going to leave you with my friend Daksh, and he's going to explain refill shuffles.
So coming to the riffle shuffle. A riffle shuffle is a shuffle where we split the deck into two halves and intermix them. The riffle shuffle where the deck is split from the middle and mixed are not preferred, because 8 consecutive perfect riffle shuffles cut exactly from the middle will eventually restore the 52-card deck to its original form. The GSR model is the more realistic model as compared to other shuffling models. It is widely used by professionals all over the world for card games and card analysis. Suppose we have A to King. We have a whole deck over here and we split them into exact two halves. From Ace to 6 is one deck and 7 to King is another deck. When we riffle shuffle them, A comes from the first deck and 7 comes from the second one when we intermix them. Now again, 2 comes from the first and 8 and 9 comes from the second. Finally, we get a randomized sequence at the end. The GSR model riffle shuffle was given by Gilbert and Shannon in 1955 and independently by Reeds in 1981. We begin by choosing a C from 0 to n according to the binomial distribution. The probability of that card is given below. Holding C cards in the left hand and n minus C cards that are left in your right, drop a card from a given hand with the probability proportional to the packet size. Chance for first card to be dropped from the left hand packet is C by n. And for the next one, it will be C minus 1 upon n minus 1 because we used the first card. An example for riffle shuffle for n is equal to 3 have been given below. Taking the first case where the deck is cut from the very beginning, we have the probability of 1, 2, 3 being 1 by 8. And for the second one, when we split it after the 1, we get 3 cases, 1, 2, 3, 2, 1, 3, and 2, 3, 1. And the probability of 1 to 3 in this will be 1 by 3. So the overall probability of the ordering will be given by using probability of cuts and the probability of the order 1, 2, 3 in each cut. For example, 1 by 8 into 1, then we go 3 by 8 into the probability of 1 by 1, 2, 3 in this particular case, that is 1 by 3, again 3 by 8, and probability of 1 to 3 is again 1 by 3, and 1 by 8 into probability of 1 to 3 here is 1. So the probabilities under riffle shuffles are as given. Coming to variation distance. Variation distance measures the distance from the randomness. The key question, what will we achieve from shuffling? Randomness of some sort. For any fixed numbers of shuffle, riffle shuffling doesn't produce complete randomness. As I earlier said, that if it's a perfect riffle split from the very middle, 8 consecutive shuffles will bring you to the initial deck. So the number of times we need to shuffle means to get closer to the randomness, which further means we need a distance between densities. So we consider Q1 and Q2 as probability densities, and the variation distance between them is told by 1 by 2 summation of Q1p minus Q2p. The half normalizes the result always to be between 0 and 1. For example, let Q1 is equal to riffle R be the density calculated above for the 3-card riffle shuffle, and Q2 be the complete reversal. The density that gives probability 1 for 3 to 1, that is certainty, and 0 for all other permutations, that is non-occurrence. So here Q1 minus Q2 will give us 1, and the densities are as far as apart as possible. Now I'll hand over to my partner Anjali to continue.
Markov chain model. So convolution method to analyze the shuffling is good and a perfect, but it doesn't help in calculating the randomness during shuffling of the cards. Markov chain analysis is a well-known process that helps in understanding the probability of each state during card shuffling. There is a Markov chain basics, a sequence x0, x1, and x2 of random variables. Each xj takes a value from some finite set S and satisfies the Markov property. Homogeneous Markov chain. The chain is homogeneous if this probability does not depend on n. There is a transition matrix explaining that. Properties of the transition matrix. Stochastic. Sum of each row is 1, that we can see from the picture. The graph representation. We can think of an homogeneous Markov chain as a random walk in a directed graph where each node corresponds to a state and there is an edge between state I to state j if Pij greater than 0. State transition matrix for top-in shuffle approach. So we use state transition matrix using Markov chain analysis for top-in shuffle, where 3-card deck probabilities and the state transition matrix are as given below. We can see from the picture that using Markov chain analysis, we were able to see the current state and the next state in the transition matrix that we were not able to see while using just top-in shuffle approach. Similarly, for state transition matrix for riffle shuffle, we could see the probabilities of the current state and the next state in the transition matrix, which we were not able to see when we just used the riffle shuffle approach, which was perfect. The transition matrix for n is equal to 3 is symmetric, but becomes non-symmetric when the number of cards are greater than 3. We can see from the matrix below that when n is equal to 7, the matrix will reach to the stable state. The graph representation. The graph shows the shuffle's x-axis versus variation distance y-axis. We can see when n less than equal to 4, the variation distance is maximum. So it's very easy to predict the outcome for a shuffle. But at around n is equal to 7, we can see the sharp drop in variation distance, means probability to predict the outcome decreases. The conclusion is it takes 7 shuffles for the total variation to fall below 0.5. The 7 riffle shuffles are usually necessary and sufficient to produce a completely shuffled deck. The advantage of using Markov chain is that shuffling n times is equal to the nth power of the transition matrix. After n is equal to 7, the transition matrix stabilizes and we don't see significant changes in the state of the matrix. This indicates that 7 shuffles are good enough to achieve the randomness. And these are the references we used to create our presentation. Thank you.